Design choices for dual-arm robotic manipulator control. I'm Alex, and I'm working with Marcel and Idan. So why dual-arm robots? You have access to a whole bunch of more diverse tasks that require cooperation between both arms, as well as increased throughput. The challenge is you have more complexity, having twice as many degrees of freedom, plus you have to plan around the other arm. So there are three possible approaches to tackling this problem. One is you have two independent controllers, one for each arm, two independent controllers with a communication channel between the two arms, and a single unified controller. So here's a demo of two independent controllers. Both controllers don't have any notion of what the other arm is doing. They're working completely independently and asynchronously. So one arm picks up objects from one side of the bin, and the other picks up objects in the other side of the bin and places them into the target bin. So here is a more detailed diagram of how we did this. We geofenced the robots. So the robot on the left picks up an object from the bottom half of the bin, goes to clearance frame 1, and then from clearance frame 1 follows the fixed path to the drop-off location. Now the robot on the right picks up objects from the top and follows a fixed path, goes to clearance frame 2, and then follows a fixed path down to the drop-off location. The advantages of this method is that it's very simple to implement, and it works completely asynchronously, so you don't have to wait for the other robot. But the disadvantages are that you have to manually define a fixed path for each new scenario, as well as the path is not ideal because you have to move out of the way to make the clearance requirements to not hit the other robot. And one failure modality is that there's a grass boundary where no robot can get to because the grippers have some finite width, making it so that some objects may not be grasped if they're right on the grass boundary.
The next approach, we kept the controllers separate from each other, but added a communication channel between them. To study this approach, we took the task of passing an object from one robotic task to another without putting it on the ground. The communication channel carries relatively simple information. After the first arm grasps the object and carries it to the location, it sends a message to the other arm that it's ready and its location. The other arm grasps the object and then send a message that the first arm should release it. The main technical challenge here is finding a good grasping pose in the air. Unlike the algorithm that was taught in the class, here the point cloud includes both the object and the gripper, and we needed to separate them before coming up with a good antipodal growth proposal. Overall, this approach allows us to have simple controllers, but that still have some cooperation between them. On the other hand, it's good only when the chance of collision is low and is not suitable for every task.
The previous methods could all solve a limited number of tasks and were not generalizable. Next, we'll tackle this problem by designing a single controller and proposing a new algorithm for path planning optimization for both arms at the same time. In this case, the benchmark consists in picking and placing multiple objects from one bin to the other. This task becomes hard because the trajectories between both arms are constantly crossing each other. In the video, you can see we successfully achieved this task, but let's look at how we solved it. The first idea was to design a state machine that forces synchronization on both arms, meaning that each arm will have to wait for the other to finish its subtask before starting the next sequence. The second idea consisted in designing two collision-free paths from one bin to the other. We propose a novel algorithm that consists in recursively finding two frames, one for each arm, so that they are not colliding, as we can see in the visualization. The main advantage of using a single controller is that now we can achieve any feasible task, and it is space efficient. However, there are some disadvantages too. The controller becomes harder to design, the optimization becomes harder too, and synchronous movements might slow down the time to success. Nevertheless, we have to say that this method is still not perfect, and we find two main issues. First is that we only constrain the end effector position to not collide, so we can still have collisions on the rest of the arm. Second, the arm gets sometimes tangled with itself due to the differential IK solver. The solution for both of these problems would be to add constraints and optimize in joint space instead of end effector space. Our algorithm could perfectly incorporate this improvement, and we leave it as future work. To conclude, in our project, we presented three different design choices of controllers of dual-arm robots. Independent controllers are simpler to program, they can work asynchronously, but are space and time inefficient. Adding a communication channel allows us to have more collaboration between the arms and solve more tasks, but the number of tasks is still limited. Finally, with a single controller, we should be able to solve any task, but the optimization problem becomes harder due to the curse of dimensionality. Thank you for listening.